Good morning, all. This is Shubham Mishra. I'm a PhD student at Clarkson University. I work with Dr. Sulafa Pitambaran. And the topic of my presentation today is ASR resistance of ground bottom ashes-based alkali-activated concrete and using MCPT for its evaluation. MCPT is miniature concrete prism test. I'll be giving a brief about everything in the following presentation. So let's come by the problem. As we know that cement is one of the widely consumed entity on planet Earth, and by 2025 this global production of cement would be as high as 4.7 billion metric tons. This motivates us to look for eco-efficient binders, and alkali-activated materials are one of such kind. Alkali-activated materials are processed using a solid aluminosilicate precursor, which is mixed or synthesized using a highly alkaline solution to produce a hardened and compacted binder matrix, which you can see here. Fly ash and GBAs have been two most conventionally and popularly used precursors in this process. But with rapid decommissioning of thermal power plants and the competitive use of slag as SCMs, it becomes a challenge to get them for production of alkali-activated materials. So we look for unconventional materials which can be used as a precursor for alkali-activated material production, and ground bottom ashes have emerged as an alternative for us. So let's look what are these bottom ashes. Bottom ashes and fly ashes both are the byproducts of coal combustion in thermal power plants. So these bottom ashes are collected at the bottom of the furnace, and whereas fly ashes are collected through electrostatic precipitators. The fact that they both are similar in the chemistry, but the exception is bottom ashes are much coarser in size. When they're ground to a finer size, they become reactive and possess all the properties of a potential SCM. So now coming to the problem of alkali-silica reaction, which is one of the key degradation mechanism in any concrete if you use reactive aggregates. Alkali-silica reaction in alkali-activated concretes become a concern because of the high alkalinity of pore solution, which is derived from high pH alkaline solutions which are used for its activation. So, but the literature which whatsoever is reported for alkali-activated fly ash and slag says that this reaction is unlikely to occur because of various reasons, one such being the reaction product chemistry, having typical limited amount of calcium hydroxide, which is one of the prerequisite in the ASR reaction. But still the question of ASR related performance for unconventional precursors remains largely uninvestigated. And here is where we get our objective from. The objective for this study is checking or detecting ASR in ground bottom ashes based alkali-activated concretes using miniature concrete prism technique. So for this study, we have taken 3 ground bottom ashes, so named GBA 1, 2, and 3, with various calcium oxide content from 2.8 to 23, which is high to low, with GBA 1 having the least one calcium oxide content. These are the mineralogical phases present in these ground bottom ashes. They all have pretty much similar size, when between 11 to 13 micron. These materials are blended with 3% calcium hydroxide and activated with a hybrid solution of sodium hydroxide and sodium silicate with the given parameters as mentioned here. So the solution to binder ratio for these mixes is 0.6, and these mixes are then tested against 3 category of aggregates with varying degree of reactivity. So these aggregates are roaring spring sand, which is a R1 moderately reactive sand, Spratt limestone, which is R2 type category, highly reactive aggregate, Job sand, R3 type, very highly reactive aggregate. So these reactive aggregates category come from C1778, and these are based on the results which we have from C1260 results for these aggregates. We used normal river sand and limestone coarse aggregate to establish control specimens and benchmark the performance of these alkali-activated concretes against them. So coming on to the method, we have used miniature concrete prism test technique. This is one of the recent techniques which have come up in the field of ASR detection. So this is documented in AASHTO T380. It overcomes a lot of deficiencies which exist in the existing test methods of ASR detection. So one such being the less effort in processing aggregates, shorter test duration it offers of 56 days for majority of aggregates. It is used for evaluation of both aggregate reactivity and efficiency of SCMs. In our case, we are using it to evaluate the efficiency of alkali-activated concretes in this same environment. The subjecting conditions are 1 NaOH solution, and the storage temperature is 60 degrees Celsius. This is the size 2 inch by 2 inch into 11 inches specimens that we cast. We use a non-reactive sand for a reactive coarse aggregate and vice versa, as quoted by the codal recommendations of miniature concrete prism test. So the failure criterion says that if your binder in combination with the reactive aggregate, it yields an expansion of less than 200 microstrain at the end of 56 days of this subjecting temperature and conditions, it can be termed as an effective binder. Whereas if it yields an expansion of more than 250 microstrains, it turns out to be ineffective. So coming on to the concrete, these are the mixed proportions which we have used here. These all mixes for alkali-activated concretes yielded a minimum strength of 40 MPa. So to establish the OPC control specimens to check how better or how worse our systems are in comparison with the OPC controls, OPC specimens, we have used the same MCPT recommendations for OPC, that are water to cement ratio of 0.45, and we have tested them against all the aggregates. This is the test matrix which we have used. We have tested all the alkali-activated concretes OPC against R0 and R2, whereas GBA-3 based alkali-activated concrete against all of them. So coming on to the results. So these are the results presented for moderately reactive aggregates. So you can see the black ones, black solid, and the broken lines are for OPC, and the green one is for alkali-activated concrete. So you can see that they showed very limited expansion in 56 days as compared to the one shown by OPC. So, and we also noticed that alkali-activated concretes, both in presence and absence of reactive aggregates, behave pretty much similar. So the expansions were quite very close. So coming on to the next, highly reactive aggregates, when we use SPRAT in combination with these alkali-activated concretes and OPC, we see that the trend is similar. We see a lot of mitigation happening as shown by the alkali-activated concretes, and if you look at the magnitudes of expansion, the SPRAT with OPC, it showed as high as 1700 microstrains, where most of the alkali-activated concretes ended up in the region of less than 200 microstrains. So the reason for this is potentially that these systems are having low availability of alkalis, low availability of calcium, and improved microstructure, which makes them stand out in terms when we compare them with OPC. So surprisingly, the results for very highly reactive aggregates, we see that OPC manifested expansions as high as 10,000 microstrains, which you can't even see here on this plot, whereas the alkali-activated concretes, they didn't show that much expansion and nothing alarming. So the point also to be noted here is that we used the solution to binder ratio is 0.6 for these alkali-activated concretes, whereas for OPC it is 0.45. It should, so despite this point that they have higher solution to binder ratio, they are not showing that much expansion. To sum up all those studied mixes and OPC's performance, this comparison is done here. You can see that plot shows these black ones, bars are showing the expansions manifested by OPC, whereas the other colorful ones are the alkali-activated concrete. To check the proneness of our alkali-activated concretes in respect to the OPC ones, the conventional concrete, we see that OPC shows significantly lesser the alkali-activated concretes are very low prone to this type of reaction. So we have compared OPC expansion at 56 days with alkali-activated concrete expansions at 56 days. So we see especially for the case of reactive aggregate 3, that is chope sand, we see that the alkali-activated concretes are 44 times less prone to ASR reaction as compared to OPC. Then we went on to compare these results with MCPT expansion. MCPT expansions with accelerated mortar bar test expansions, those are C1567 expansions, and we got a very good coefficient of correlation as high as 0.95. So these test results correlate really well. The 14-day expansion showed by accelerated mortar bar test and 56 days expansion showed by MCPT. They correlate really well. And both the test results indicate that these alkali-activated concretes based on ground bottom ashes, they significantly have a higher resistance to ASR as compared to the conventional ones. So to summarize everything what I presented, we noticed that all the tested alkali-activated concretes gave us superior resistance to ASR as compared to the conventional ones. The conventional ones expanded evidently, and this is due to the presence of expansive ASR gel. The potential reason of alkali-activated concretes performing so well was that they have high alkali binding in their microstructure, low levels of calcium present in them, and the refined pore structure. So we can say that these alkali-activated concretes can be used as an ASR mitigation strategy in locations where the construction activities are only constrained to use of reactive aggregates. MCPT, even though with the conservative threshold of very thin band, if you have seen the 200 to 250 microstrains, suits apparently the context of predicting ASR in ground bottom ashes based alkali-activated concretes. And ending, we didn't see any visible signs of de-stress for these alkali-activated concretes. The future works in this would be correlating the pore solution chemistry with the ASR behavior, and also the relating surface and bulk electrical resistivity parameters with ASR. I would like to acknowledge FHWA for funding, Penn State and Purdue University for collaboration, and Camp Clarkson University for helping us with all the analysis. Thanks for your attention.